This is a story for one of the homework problems that is in the lawn kappa work. So in this problem, you're drilling holes in a circuit board by an automated machine, and so you want the hole to be right here, but there's lash or backlash in the machine, and so you have some error because the gears that control the position of the drill bit don't actually touch each other. They slip a little bit. And so the way that those two errors are represented are as two-dimensional vectors. So one error you could say is this S1, so that's a shift number one, and another error is shift number two, right? So right there. So the total error is going to be the vector sum of those two. Now, the way that the problem is structured, there's a random angle between these two errors. And so that random angle can be anywhere in the circle, right, all the way around 0 to 2 pi. So how far off are you on average? So how big is this r vector on average? So one way of thinking about that is a vector sum, find the magnitude of this vector. So here's S2. So S2 is made out of an x piece and a y piece. And with a little trigonometry, you can say that S2 in the x is S2 cosine theta, and S2 in the y is S2 sine theta. And so if you rewrite this S2 vector in an x component that's parallel with S1 and a y component that's orthogonal to S1, you can say that the three sides of the triangle, so r is the hypotenuse, S2y is the vertical, so that'd be S2y squared. And the horizontal is S1 plus S2x squared. Now, when you follow the algebra through that and expand out the expression, collect the terms that are like, what you get is something that looks kind of like the Pythagorean theorem. So the radius so that's the magnitude of the total error, so that would be r squared. And then you have x squared and y squared, kind of, right? So it looks kind of like a squared plus b squared equals c squared, right? Except you have this cross term, 2 s1, s2, cosine theta. Now, the best way to believe in math like this is just to work out the algebra yourself. It helps a lot. So in the end, you have this expression that the magnitude of the total error is the square root of the first error source squared, the second error source squared, and then if you want, you could almost say this is like a covariance term. So 2 s1, s2 cosine theta. Notice the theta is not squared. So that's our error, and we want to find out what that error is, that total error is, on average, for any old hole you drill. How do you find the average value of an error? So if you've studied Calculus 1 and you're in Calculus 2, here is method number 1. If you want to find the average value of something, just take an integral over a region and then divide by how long the region is. So here's the blue graph is the graph of sine. And if we want to find the average value of sine from 0 to pi, you can take the integral, which is a mathematical operation that finds how much area is underneath this graph. And then you divide by the region length. Now, in this program Mathematica, you can take that integral really quickly. I don't know what that means. And you get that it's 2 over pi, which numerically is about 0.63. So again, we're finding the average value of this sine function. So here's sine. The average value is 0.63. I plotted it right here. And you can see that this orange line is, it reminds you of the average value of the blue line. But what we want to average is this radius. So I switched from the S1 language to a squared and b squared. So here is what we can do. I'm just going to take away some distraction. here's what we can do. We can take the radius, right? So there it is, a squared and b squared and 2ab cosine theta. So this is the radius function. We can take an integral all the way around the circle from 0 to 2 pi, and we can divide by 2 pi d theta. And this integral, it's called an elliptic integral. There are tabulated forms of it. It's not a trivial thing to work out by hand. But Mathematica can compute it very quickly for you numerically. So if A is, let's say, 10, and B is 10 and a half, and we run it, so Mathematica outputs the 10 and the 10 and a half, and then Mathematica figures out, okay, so if one error is 10 centimeters and the second error is 10 and a half centimeters, then on average, the total error you'll have from those two sources is about 13 centimeters. Now, if you haven't taken Calc 1 yet, this probably sounds like a bunch of gibberish. And so in a minute, I'll show you how to evaluate this source of error by just drilling a lot of holes in the circuit board.